Hello, this is Professor Oaks, and in this video we are going to talk about the mean value theorem. So let's start by talking about a different theorem here called the extreme value theorem. And it says that if a function f is defined and continuous on a closed interval from a to b, then f takes on a maximum or largest value at some number in that interval a to b and a minimum or smallest value at some number in that interval a to b. So let me look at the two conditions here. The function needs to be defined and continuous. So let's actually look at an example of what this might look like. So here is an interval from A to B, and here is say f of A, and here is f of B. So here is f of A, and here is f of A. Here is f of B, and then you can see then that, well, if the function happens to be defined and continuous in the interval, then of course here is the minimum and here is the maximum. All right, now let's say that you have something where maybe A is here, and B is here, and this is f of A, and this is f of B. Here's something else that could happen, right? So the maximum, minimum don't necessarily have to be at those endpoints, but it could be down, and then up, and then back down. Well, does the function f look like it's defined and continuous on the closed interval a to b? Yes. And so that means, well, here is the minimum, here is the maximum, and there's still a maximum and a minimum here. Now, let's say, for example, you have something that looks like this, and here's A, here's B, but the function is defined at B, but there's, say, an asymptote at A, and then you can see here that the function is not continuous at x equals A, and therefore you see, well, this had a maximum, but it didn't have a minimum. All right, so it f, so f, I'll call it f, all right, we'll just call this f, does not have a minimum on A to B. So there's lots of scenarios that can happen, but just remember that the function f needs to be defined and continuous on that closed interval A to B. Let's talk about Rolle's theorem. So if f is continuous on the closed interval A to B and is differentiable on the open interval A to B, and if f of A is equal to f of B, then there's at least one number C in the open interval A to B such that the derivative, the first derivative at that number C is equal to 0. All right, so let's look at an example here. So here is the closed interval A to B, and you can see that, one, this f is continuous on A to B, and it is continuous on A to B, but then it is, and I was going to check the next condition now, and then it is differentiable on the open interval A to B. And so then f of A is equal to f of B, which is equal to D in this case. So f of A equals f of B, which is equal to D. Then there's at least one number C, and here it is where the first derivative at C is equal to 0. And you can tell here that the slope of the tangent line at that point is 0. So at this point, f prime of C is 0. All right, let's try another example here. Here we see that, well, f is continuous on the closed interval A to B, but we can see that f is not differentiable at let's see, C. And you can see here is the point where the a graph would have a vertical tangent line. So not differentiable here due to the vertical tangent line. And by the way, there is a way for you to sort of visualize these, and anytime the graph comes to a sharp corner or a sharp point like this, then that would be the case. All right, so let me give you one more example, and I'll sketch it off here to the side. And here we have, say, A, and we have B, and, well, then let's see, let's draw a function that might look like this. And here is f of A, here is f of B, and we see that f is continuous on the closed interval A to B. All right, we can see that right here. And we can also see it is differentiable on the open interval A to B, but f of A does not equal f of B. So let's just recap here then. In this case, Rolle's theorem does not apply. Here in this case, Rolle's theorem does apply, and in this case, Rolle's theorem doesn't apply. What a time to be alive. I hope that you now see the different situations here with Rolle's theorem. So, in this next example, explain why Rolle's theorem does not apply to the function even though there exist A and B such that f of A equals f of B. So here you can see, well, the function is not differentiable at x equals 1. And if you look here on this side of 1, the slope is 1, and on this side of 1, the slope is negative 1. All right, so the derivatives from the left and the right of 1 are not equal. Here we have, let's see, oh, f of x is cotangent of x over 2. Well, all right, you can see right here that this is not continuous at x equals 6. All right, here, let's do another example here. So here is another example of a function that is not continuous. So not continuous at x equals 0. So f of x has a vertical asymptote here. And here's a function you don't see every day, but here is another function where there is a vertical tangent line at x equals 0. So not differentiable at x equals 0, or f of x has a vertical tangent line at x equals 0. I hope that you enjoyed that example. Now, we're going to determine whether Rolle's theorem can be applied to f on the closed interval a to b, and if Rolle's theorem can be applied, then we're going to find the values of c in the open interval a to b such that the derivative at c is equal to 0. All right, so remember there are a couple of things that we need it to check for, and one of them is whether f of x is continuous on the closed interval 1 to 4. And I know that that is yes, because it is a polynomial. Then I need to know if f differentiable on the open interval 1 to 4. And I know that is yes, because it's a polynomial. And now I want to know, is f of 1 equal to f of 4? Well, 1 squared minus 5 times 1 plus 4. That is 1 minus 5 plus 4. So that is 0. And f of 4 is 4 squared minus 5 times 4 plus 4, 16 minus 20 plus 4, 0. So yes. And now that means I want to find the values such that f prime of c is equal to 0. Well, f of c is c squared minus 5c plus 4. So f prime of c is 2c minus 5. And I'm going to set this equal to 0. So 2c is equal to 5, and c then is equal to 5 over 2. So 5 over 2 would be the point where the derivative is equal to 0. And by the way, of course, I just said that Rolle's theorem applied, right? So just keep that in mind, and if I want to make a sketch of this to figure out if what I said is all true, well, then f of 1 was 0, and f of 4 was 0, and I know that, well, f of c is one of the points on the graph, and I know that this had a y-intercept of 4, so 1, 2, 3, 4. All right, and this is a parabola, so I can draw this by symmetry. But if I want to find f, then at 5 over 2, I have 5 over 2 squared minus 5 times 5 over 2 plus 4. And that is going to be a negative 9 over 4. I'll leave that arithmetic up to you now. So at 5 over 2, I have negative 9 over 4. And here is the parabola. And at this point, you can see that the slope of the tangent line was 0. And that actually happened to be the minimum of this parabola. So now, let's try another example. So we have f of x is x minus 3 times x plus 1 squared on the interval from negative 1 to 3. So let's see if Rolle's theorem applies. So is f continuous on the closed interval from negative 1 to 3? Well, yes, because it's a polynomial. You could multiply this out, but I'm not going to do that, at least not right now. And 2 is f differentiable on the open interval from negative 1 to 3. Yes, because it's a polynomial. And 3, does f of negative 1 equal f of 3? Well, negative 1 minus 3 times negative 1 plus 1 squared, that will be negative 4 times 0 is 0. And f of 3 is 3 minus 3 times 3 plus 1 squared, 0 times 16, 0. So yes, these are equal. So Rolle's theorem does apply. All right, so please keep that in mind that we were checking to see if Rolle's theorem applies. So now we want to find C such that f prime of C is equal to 0. So f of C is C minus 3 times C plus 1 squared. And f prime of C, then we need to use the product rule. So product rule, and the U is C minus 3. The V is C plus 1 squared. So U prime is 1. V prime is 2 times C plus 1 to the first power times 1. So remember to use the chain rule here. So the derivative is VU prime plus UV prime, which is, let's see, C plus 1 squared plus C minus 3 times, and I'm going to write this as 2C plus 2. All right, so I'll distribute this 2 right here. And now, well, I want to actually, remember, set this equal to 0. So I want to multiply all of this out. So we have c plus 1 times c plus 1 plus, let's see, 2c squared plus 2c minus 6c minus 6. Distribute here as well. So c squared plus c plus, let's see, c plus 1 plus 2c squared minus 4c minus 6 equals 0. Combine like terms, 3c squared minus 2c minus 5 equals 0. And now I can factor or use the quadratic formula or whatever way that you feel comfortable solving this quadratic equation. You do what's best for you in this situation here. So you do you, okay? So now let's factor this. 3c minus 5 times c plus 1 equals 0. So set each factor equal to 0. 3c minus 5 equals 0. And c plus 1 equals 0. So if you add the 5, you get 3c is 5 and divide by 3. So c is 5 over 3. And then for this equation here, or this factor here, you can subtract the 1 and get c is equal to negative 1. And then you can see that, remember, for Rolle's theorem, the c value needed to be in the open interval from a to b. And so c equals negative 1 is not in the open interval from negative 1 to 3 because it's one of the endpoints of the interval. And so therefore c equals 5 over 3 is the solution we're looking for, because this is in the interval, the open interval from negative 1 to 3. All right, so what a time to be alive. Let's go ahead and try another example here. So f of x is cosine of x on the interval from 0 to 2 pi. So let's check the conditions. Is f continuous on the closed interval from 0 to 2 pi? And of course, yes, it is one of the trigonometric functions here. 2. All right, so yeah, so again, the domain of cosine of x is negative infinity to infinity. So of course it is continuous here. And so is f differentiable on the open interval from 0 to 2 pi? And well, yes. All right, because, well, if you notice, f prime of x is negative sine of x, and also the domain of negative sine of x is also negative infinity to infinity. And 3 is f of 0 equal to f of 2 pi, or does cosine of 0 equal cosine of 2 pi? Well, yes, these are both equal to 1. So therefore, Rolle's theorem does apply. All right, so Rolle's theorem does apply. So now we're going to find the c such that, I'll rewrite that, such that f prime of c is equal to 0. So here we have f of c is cosine of c. So f prime of c is negative sine of c. I'll set this equal to 0. So sine of c is equal to 0. And then I know that sine of c equals 0 when c is equal to 0, pi, or 2 pi. But the only one of these numbers in the open interval from 0 to 2 pi is pi. So c equals 0 and 2 pi are not in the interval from 0 to 2 pi, or the open interval from 0 to 2 pi. So that means that the solution is c equals pi. So hopefully you are getting a sense of how to check these conditions here. So one condition for f of x is secant of x on pi to 2 pi. So is f continuous on pi to 2 pi? And the answer would be no, because the f of x equals secant of x, or 1 over cosine of x, has an asymptote, and specifically a vertical asymptote at x equals 3 pi over 2. All right, and you can see that here because cosine of the 3 pi over 2 would be 0. So 1 over 0, undefined, and there is your asymptote. So that means Rolle's theorem does not apply here. So let's do another example. E. All right, f of x is equal to x squared minus 1 over x. And I think you can see here that on the interval from -1 to 1, the f is undefined at x equals 0. So is f continuous on the closed interval of -1 to 1? No, because the x equals 0 is not in the domain of f of x. What a time to be alive. All right, so let's try another one here. We have f of x is equal to x minus 2 times the natural log of x. And we want the interval from 1 to 3. So 1 is f of x continuous on the closed interval 1 to 3. Well, yes, because I know that the domain of the natural log of x is actually x is greater than 0, and we're only looking on the interval from 1 to 3. All right, so, and then is f of x differentiable on the open interval from 1 to 3? Well, let's see. Well, f of x was x minus 2 natural log of x, and f prime of x then would be, well, the derivative of x is 1 minus 2, and the derivative of the natural log of x was 1 over x, so 1 over x. And so we see that, well, the derivative is undefined at x equals 0, but 0 was not in the interval that we were looking at. So f prime of x undefined at x equals 0, but 0 was not in the interval from 1 to 3. But x equals 0 is not in the interval from 1 to 3. All right, now we need to find out, is f of 1 equal to f of 3? Well, f of 1 is 1 minus 2 natural log of 1. So that's 1 minus 2 times 0, which is 1. And f of 3 is 3 minus 2 natural log of 3. And if I actually do this, I get something that is about 0.803. I did that mentally, or you can just use your calculator to get a quick estimate, but I hope that you see that this is definitely not equal to that approximately 0.803 here. So this is definitely no, and so since these were not equal, that means therefore Rolle's theorem does not apply. What a time to be alive. All right, so let's try another example here. This is a piecewise function. So let's see, we are going to look at this. Let me tell you here on the interval from 0 to 2. So first question, is f continuous on the closed interval 0 to 2? Well, how would you know? Well, you need to, well, you could graph this. So if you took a sketch of this graph, all right, and remember we only want from 0 to 2. So if x is less than or equal to 1, we have x, so x, y at 0, we have 0. At 1, we have 1. So 0, 0, 1, 1. And this is what this looks like. And now, if x is 1, y would be negative x plus 2. So that will be negative 1 plus 2 is 1. And then at 2, we have negative 2 plus 2, 0. And we see that, well, this is continuous because we can actually see that the limit as x approaches 1 from the left of f of x will be the limit as x approaches 1 from the left of x, which is 1, and the limit as x approaches 1 from the right of f of x would be the limit as x approaches 1 from the left of negative x plus 2. So it's negative 1 plus 2, which is 1. And so we see that the limit exists. So the limit as x approaches 1 of f of x exists because these right and left hand limits are the same. And we see that f of 1 is equal to 1. So therefore this is continuous. Now, is f differentiable on the open interval from 0 to 2? Well, let's see here. At x equals 1, the derivative from the, let's do the left first of x. That will be the derivative of the x. All right, so that would be 1. And then the derivative from the right would be the derivative of the negative x plus 2, which is negative 1. So therefore, the left and the right hand derivatives at x equal 1. All right, so again, this is all for x equals 1 here. So I don't want, I don't even need to say that, I don't think, again. So therefore, this is no, because these are not the same. So therefore, Rolle's theorem does not apply. What a time to be alive. All right, so let's do another theorem here, the mean value theorem. So this is very similar to Rolle's theorem because f has the continuous on the closed interval from a to b. That was the first thing, same thing. And differentiable on the open interval from a to b. That's the second thing. Well, then there has to be a number c in the open interval a to b such that f prime of c is equal to f of b minus f of a over b minus a. But notice, if f of b equals f of a, then the f of b minus f of a over b minus a is 0 over b minus a, which is 0, and that's what Rolle's theorem says. So if these are equal, then you get Rolle's theorem, all right? So just, again, if you didn't notice, if you subtract f of a from each side, here you get f of b minus f of a is 0. Then you substitute the 0 in here. You get 0 over b minus a, which is 0. And this is Rolle's theorem, all right? So mean value theorem is actually just a more general case. And we don't really need to use Rolle's theorem very often because of this. All right, so you can see an example here of what is actually going on, but let's look at the next page and do an example here together. So copy the graph and sketch the secant line to the graph through the points A, f of A. So here's A, so here would be f of A. So this will be the point A, f of A, and B. And here is the point f of B. So here would be the point B, f of B. Then sketch any tangent lines to the graph for each value of C guaranteed by the mean value theorem here. All right, so let's draw the secant line through these 2 points here. So here we go. And this, again, is the secant line. And then if I look here, I can indeed find tangent lines to the curve here. So here it is. So here it is. So here's one of the tangent lines, and it's right here. And so this is one of the C values. And then here is another one of them. All right, so here is another one right here. Right here, so this is, say, C1, and that could be C2. So you can see that this is a tangent line, and this is a tangent line, and there are actually, in this case, 2 lines. All right, so 2 tangent lines. So I'll write that more explicitly. 2 tangent lines with the same slope as the secant line. What a time to be alive. All right, so explain why the mean value theorem does not apply to the function f on the interval from 0 to 6. Well, here I can see that the function f is not continuous at x equals 2. And here, f is not differentiable at x equals 2. All right, so you're going to see a sharp corner, a vertical tangent line right there. All right, so now let's try again with another problem. Determine whether the mean value theorem can be applied to f on the closed interval from a to b, and if the mean value theorem can be applied, find all values of c on the open interval a to b such that f prime of c is equal to f of b minus f of a all over b minus a. All right, so let's do this today. All right, so 1 we see is f, let's see, continuous on the closed interval 0 to 1, yes, because it's a polynomial, and 2 is f differentiable on the open interval 0 to 1, yes, because again, it's a polynomial. And now, guess what? We can see whether we can find this value easily or not. So remember that we don't necessarily need to check that f of b equals f of a here, because we're just trying to figure out the c value that would give this value, not necessarily whether it's 0 or not. All right, so we have, let's see, f of c is c to the third. F prime of c is 3c squared. F of b would be, well, remember, this is a and b, so f of 1, so that's 1 cubed 1. And f of a will be f of 0, which is 0 cubed, which is 0. So let's see, what do we need? We need f prime of c, so 3c squared is equal to f of b, 1, minus f of a, 0, all over b minus a, 1 minus 0. So 3c squared is equal to 1. Then divide by 3 to get c squared is 1 over 3. Then c is plus or minus the square root of 1 over 3. But notice that c equals negative square root of 1 over 3 is not in 0 to 1. So the solution is c is the square root of 1 over 3. All right, what a time to be alive. Let's try another one here. So, is f continuous on the closed interval -7 to 2? Well, if you look at this, this is under the square root, the 2 minus x. So 2 minus x has to be greater than or equal to 0. So subtract the 2, negative x greater than or equal to -2. And then divide by -1 and change the inequality sign. So x is less than or equal to 2. So we see that this is continuous here because the function is smooth and defined on the interval. So now we need to find out, is f differentiable, right, on the open interval from -7 to 2. Well, f of x was the 2 minus x to the, well, I'll write the square root is the 1/2 power, and then the derivative f prime of x is 1/2 times 2 minus x to the negative 1/2 power. Use the chain rule, so the derivative of 2 minus x is -1, so this becomes negative 1 over 2, and I'll bring this part back into the denominator as the square root, so 2 minus x to the 1/2 power, or negative 1 over 2 square root of 2 minus x. Now, I do know that x cannot equal 2 because that would make the denominator equal to 0. However, 2 is not in the open interval of -7 to 2. So that means this is, f is differentiable on that open interval. So now I need to find f prime of c, which is -1 over 2 square root of 2 minus c. And then remember, a was -7, b was 2, so I need f of b, so that's the square root of 2 minus 2, which is square root of 0, 0, and f of a will be square root of 2 minus -7, that's square root of 9, which is 3, and then I solved this equation for c. The f prime of c is f of b minus f of a all over b minus a. So f prime of c was -1 over 2 square root of 2 minus c. F of b was the 0. F of a was 3. B was 2. A was -7. So I have -1 over 2 square root of 2 minus c is -3 over, let's see, 9. And you can reduce this fraction first if you would like. So why don't we do that? -1 over 2 square root of 2 minus c is -1 over 3. Then solve this however you want. But if you notice, the numerators are the same. So all you have to do is set the denominators to be equal to each other. So 2 square root of 2 minus c is equal to 3. Then I will go ahead and square each side. So 2 squared is 4. Square root of 2 minus c squared is 2 minus c, and 3 squared is 9. Distribute the 2. So 8 minus 4c is 9. Subtract the 8 to get 4c is 1. And then divide by let's see, what is it? 4, sorry, -4, so c is -1/4. And there you go. That is the solution. The c value that is guaranteed here. So now there are some other problems that you could try here if you would like to. If you really enjoyed the mean value theorem, which I hope you did, and hopefully you are already looking forward to the next video. Thank you and have a great day. What a time to be alive.